Assalamualaikum. My name is Muhammad Afiq Adam bin Muhammad Adnan, A163655. I'm here to do a presentation about introduction of this project. Okay, first of all, this project is to design proportional controller, P controller. In P controller, it uses a non-inverting amplifier with a closed loop system. In general, the mathematical equation representing a given system that serves as a basis for a simulating model can be derived from physical laws. In this page, we will demonstrate how to derive mathematical model and then implement the model in Simulink. By using Simulink, it's very straightforward to present and then simulate a mathematical model representing a physical system. Models are represented graphically in Simulink as block diagrams. A wide array of blocks are available to user in provided libraries for representing various phenomena and models in a range of formats. One of the primary advantages of employing Simulink for the analysis of dynamic system is that it allows us to quickly analyze the response of complicated systems that may be prohibitively difficult to analyze analytically. Simulink is able to numerically approximate the solutions to mathematical model that we are unable to solve. For the main objective is to design a proportional P controller that regulates the angular velocity of the motor such that it remains constant despite the presence of unmodeled dynamics, noise, perturbations. The target specifications are 1. Steady state angular velocity, which is equals to 25 rad per second. Steady state error, which is plus minus 20%, and maximum overshoot less than or 45%.
Hi, I will explain about tachometer calibration. Firstly, we enter the word input for 15 words. So, the block diagram will show the Vt and omega m. With the equation, we can get the value of Kt. The value of Kt is 0.0625. Using interpolation, we get the value of Vt for one word. So, after that, we can find the Vin at 42 rads per second because 42 rads per second equal to 400 rpm. So, we search it with 42 over 0.0499, which are the value of input of one word. So, we get the 842 word, which are the Vin when we can get the value of 42 rad per second. Here are the block diagram of 842 word. We can get the Vt equal to 2.6757 and omega m equal to 42 rad per second. To make sure our experiment is correct, we plot a graph angular velocity against the tachometer output voltage. So with that, we calculate the value of the gradient, which are the value of Kt. So we get the value of Kt equal to 0.0625, which are equal to our Kt at the previous slide. So we assume that our experiment is correct. Next, I will move to the topic of modeling of a DC motor. So we choose Vin equal to 5 volt. Here is the block diagram and oscilloscope graph for the 5 volt input. Next, we calculate the Vt at the settling time, which are at 63%. So to search for the angular velocity at the settling time, 63% need to start with the V angular for the 5 volt. So we get the result and we place the tracker at our result, so we get the time. Next, after we get the time, after the settling time, we have to find the value of A, which the formula 1 over t time for the settling. So after that, we find the value of km, which are the A times with the 0.01559, which are the word out of the system. Next, we use the general form of the transfer function and substitute the value, and we use the Laplace transform and get the Vt equation. Lastly, we search for the steady state speed of the motor when t equal to t is calculated. So omega m equal to 0.2494, that was given in the block diagram of 5 volt, and we times with the 0.63, which are the percentage of the sampling time.
Next, we are going to talk about closed loop in control DC motor. In this part, we built the closed loop system without corrector in order to calculate the actual error of the system. Using the voltage, which is 3 volt, to have 750 revolution per minute as the reference set point signal, and the tachometer output signal as feedback to build the closed loop. In this experiment, we use 4 types of resistance, which are R1 is equals to 1000 ohm, R2 is equals to 1000 ohm, and R3 is equals to 500 ohm, and R4 is equals to 500 ohm. In order to find the actual percentage error of the system, we use MATLAB to find VE, and according to the graph that we have calculated, the VE that we get is equals to 2.9908. So the actual percentage error of the system we get is 0.3067%. After that, we create a closed loop system with calculating a suitable value for proportional gain Kp such that the steady state error is minimized to less than 5% as per requirement. And the value of the Kp that we obtain is 0.9771. Next, we find the value of Rv to have the correct gain Kp when the value of R5 is fixed at 10 kilo ohm. According to the formula given, we are able to find the value of Rv, which is equal to 229 ohm. Next, the block diagram is edited to the calculated value of resistor, and 492 voltage of input voltage is set in order to get 25 radian per second for angular velocity.
In this part, we will examine how the controller design in the previous section behave when the controller is subjected to the value of t more and equal to 5 second disturbance. The controller setup and results of the effect of the disturbance are shown in figure here. Here we can see the block diagram used for the open loop control with input voltage set up to 500 volt to the given output of 25 radians per second. Here we can see the block diagram used for the open loop control with the input voltage set up to 500 volt to the given output of 25 radian per second. The radio of oscilloscope indicate the output given in the applied disturbance. The result that have got shown a stable graph since the disturbance is not strong enough even it is already updated to the latest value of 14 to show the visible impact. We can conclude that there are some shift between the first cursor and the second cursor through 5 seconds to 15 seconds.
Alright, next we will explain about the closed loop system. We also use a design closed loop controller that we design and we impose the same disturbance at time more than 5 seconds. So by using we are using a calculation proportional gain Kp and other value of resistance that required in the summing junction. So as you can see from the diagram, there is a feedback system that we impose because it is a same loop system, and for this we only require about the 472 volt input voltage because it required much less input to achieve 25 radian per second. Also, we put a proper resistance which is R1 and R2. We put about 1 kilo ohm, and R3 and R4 we put about 500 ohm, and R5 put about 10 kilo ohm, and after we are doing a calculation of RV, so we get RV is about 292 ohm. Next, we are moving to the analysis oscilloscope graph. We can see with the final value of 25 radian per second, we can see that there is no significant ripple in the diagram, and we believe that the system with the disturbance for time that more than 5 seconds is not strong or visible enough to create a ripple in this graph. So after doing about the 5 time run the program, we still get the same analysis, same oscilloscope analysis graph. Thank you.
No, by using PID controller. PID controller is a proportional integral derivative controller, which is a control loop mechanism employing feedback that is widely used in industrial control systems. A variety of other applications requiring continuously modulated control. A PID controller continuously calculates an error value. This is the example of the mechanism of PID controller. That's all for the conclusion. In a nutshell, we can say that we have met our objectives. The proportional P controller that regulates the angular velocity of the motor have been designed into 4 different types of model, which is L1, L2, L3A and L3B. We also managed to learn how to calibrate the technometer by using calculation for model L1. We managed to regulate and control the speed of motor by inserting the voltage value into the input terminal. Model L1, L2, L3A and L3B have different voltage input value due to different values of resistor. This leads to different value of consistent KT. Thank you so much.